Have you ever wondered how a machine can learn to think? Machine learning research is the art and science of teaching computers to learn from data, without being explicitly programmed for every single task. An ML researcher is an explorer, charting new territories in artificial intelligence. Their core mission is to design and test new models, pushing the boundaries of what machines can perceive, understand, create. It's less about writing simple code and more about asking profound questions about intelligence, framing those questions so a computer can begin to comprehend, and patiently guiding the machine through trial, error, meticulous refinement. This role isn't just improving systems, it's inventing new capabilities. It's a cycle of curiosity, creativity, and rigorous validation. Researchers may spend weeks on a single complex problem, breaking it into smaller pieces. They read academic papers, brainstorm with colleagues, and sketch models before any experiment runs. The goal: discover a new algorithm, a more efficient architecture, or a better way to handle data. Share it with the community, and eventually build it into products that shape our world. The work demands the logical precision of a mathematician, the creative problem-solving of an engineer, and the patient observation of a scientist. A researcher's day often begins not with a computer, but with a question. This question is the seed from which all subsequent work grows. It might be technical. Can we cut compute cost by 30% without losing accuracy? Or conceptual. How can a model explain its own reasoning in plain English? Sharpen the question into a concrete, testable idea. Define the problem and the key variables. Formulate a clear hypothesis. Often it's a new architecture or a novel modification to an existing one. Ground it in literature and ensure it's genuinely new. Example: by adding a tension mechanism X to model Y, fraud detection improves by at least 5%. Specific, measurable, actionable. The heart of the work: data, models, and experiments. Data is the fuel. Quality determines outcomes. Gather images, text, sensor readings, numerical records, often messy and incomplete. Meticulous cleaning, correct errors, handle missing values, remove outliers. Split into training, an optional validation, and a held-out test set for an unbiased evaluation. Build with Python, TensorFlow, or PyTorch, turning design into code. Train on GPUs for massive parallel computation. Monitor progress. Tune hyperparameters like learning rate and depth to improve validation performance. Finally, evaluate on the test set and log everything for reproducibility. An experiment in action: detecting financial fraud. Build a better model to flag fraudulent credit card transactions. Millions of past transactions provide the ground truth. Question: can a graph neural network beat a decision tree by using relationships between transactions? Rigorous setup: clean data, fix missing amounts or vendor info, engineer useful features. Frequency spikes and average spend become signals. Split 80-10-10 for train, validation, and a pristine test set. Train both models on the same data. Tune hyperparameters for each. Evaluate on unseen test data. If GNN hits 95% with fewer false alarms, the hypothesis is validated. Measuring success is multifaceted, beyond a single number. High accuracy can mislead in imbalanced problems like fraud. Speed matters. Real-time systems demand low inference latency. Some applications require decisions in milliseconds. Find the optimal balance for the use case. Fairness is non-negotiable. Evaluate across subgroups to avoid bias. Models must not perpetuate historical inequities. Test safety and robustness under adversarial and noisy conditions. Build safeguards to prevent harm. True success balances accuracy, speed, fairness, and safety. No researcher works in a vacuum. The human element is critical. Collaboration with software and DevOps ensures models can be built, scaled, maintained. Product partners align research with real user needs and business goals. In specialized fields, domain experts frame questions and interpret results. Clear, ongoing dialogue bridges lab and real world. Researchers carry ethical responsibility, mitigate bias, protect privacy, design safeguards. The loop: ask questions, design experiments, test against critical metrics. This collaboration drives smarter, more efficient, safer systems. Curious, collaborative, ethical. They are the architects of our future.